After a brief interruption, we're back. So, we just figured out what the forces were that were acting on the rocker of this mechanism. A 9 Newton force coming from the bearing, a 7 Newton force coming from the coupler, and the applied force of 10 newtons. The next thing to draw a free body diagram of is the coupler itself, body 2. And we don't have to worry too much about its shape and location at this point, because we know that this is just a 2-force body. It's got an equal but opposite reaction force, F3.2, which is operating along its axis, and that is 7 kilonewtons or 7 newtons. And as this is a 2-force body for static equilibrium, it has an equal but opposite force acting at the other end. These two forces have lines of action that are identical. This is F1.2, also with a magnitude of 7 newtons. So now we get to the last portion, really the exciting portion of this whole thing. I know you're all waiting with great anticipation, and that's the crank. And the crank is going to be a member that has two forces acting on it, a reaction force coming from the coupler, and a bearing force coming from O1, and there will be an applied torque. So first things first, I'm going to use my two triangles again, and I will transfer this line down parallel to the original, and I will again make sure that the line is at the same scale as the original drawing, 10 millimeters. So my line goes from there to there. I have to erase a little bit of it. And double check. It's 10 millimeters long. Now, this line is going to have a force coming from the coupler that will be parallel to that coupler. So again, I am going to use my triangles and get my line of action. And take advantage of the fact the triangles are already there and sketch in line of action for the bearing force. So, I will have two forces acting on this piece, equal and opposite, but as you note, their lines of action are somewhat off. So, that tells me that I will have a couple on this body for static equilibrium. And what I'm doing right now is determining the moment arm that is perpendicular to the lines of action of the force, so that I can calculate the torque. So, I know that I have a 7 Newton force here, and this is F2.1, and I have an equal but opposite force of 7 newtons here, F0.1. Because the lines of action of these two forces are displaced by this distance, I have an applied torque. I've got a couple. So, if I measure that distance, I get 5 millimeters. Therefore, I know that my applied torque must be 7 newtons times 5 millimeters, or 35 Newton millimeters. Hopefully that's visible on the sheet. But that concludes this problem. So as you can see, it's fairly easy to go from a sketch that is at 1-to-1 scale, use that scale to our advantage, use triangles, transfer lines, come up with the forces, and then use free body diagrams for each of the bodies, along with, again, drawings to scale, in order to get the torque that must be applied to this mechanism at the crank in order to keep it in static equilibrium with a 10 Newton force applied at this angle to the crank, to the rocker. So that concludes this problem. I will be continuing to do some additional problems and posting them as time goes on.